In this video, we show real-life applications of the previously discussed theoretical parts.
Yes, we'll examine the timer module and the Watchdog Timer and demonstrate how the example programs work. By the end of the video, you'll be able to configure timers yourself to incorporate these useful modules into any of your own projects.
Let's not spend more time, get to work. In the first example, we will flash an LED by the counter and timer module every second. In the following, we will explain step by step the functionality of the program to be written and the necessary settings.
As a first step, let's create a new project in the STM32Cube IDE development environment for the microcontroller on our board. This can be done by clicking on New STM32 Project in the File menu. From the part number drop-down menu, select the STM32F446ZET6 microcontroller and click on it in the MCUs MPUs list, and then click on Next to continue.
I've done it. Name your project whatever you want, then click on Finish. This will create the configuration file, which we will work with in the next few steps.
On the Nucleo development board, the microcontroller receives an 8 MHz clock signal via the built-in ST-Link to the HSE input. To use this, select RCC from the System Core menu and change the high-speed clock setting to bypass clock source. This is necessary because typically using external clock sources can produce a much more accurate clock signal compared to oscillators integrated into the microcontroller, which has a major impact on our timings. Further clock settings are made in the Clock Configuration tab. We need to change the input frequency to 8 MHz since this is the frequency of the external clock source in the development board. In the System Clock Mux, select HSE, which is the high-speed clock that was set before. This will cause the clock signals APB1 and APB2 used by the counter and timer modules to be based on the external clock source.
Return to the Pins and Configuration tab, and from the Timers menu, click on TIM1. Set clock source to internal clock, so that the TIM1 module will work from the clock signal generated by the microcontroller.
The 1-second timing can be achieved by the following settings. In Parameter Settings, change the prescaler to 127. The actual prescaler, in this case, will be 128, because setting the prescaler register to 0 will result in the original clock signal without a prescaler, meaning a division by 1. The counter period is configured to 62,499. In this case, we have to keep in mind that the interrupt event is generated when the module counts up to the set value and then turns to 0, meaning 1 additional clock cycle elapses. The length of the timing can be checked using the formula shown in the first video. Let's put the configured values in the relation. So 127 plus 1 will be the prescaler, which is equal to 128. Multiply this by the limits defined by 62,500 and divide the results by the 8 MHz frequency of the clock signal, expressed in Hertz for SI units. The result of these calculations gives a timing of 1 second.
As the next step, within NVIC settings, check the TIM1 update and TIM10 global interrupt option to be notified when the set timer expires.
We have connected the LED to the PD7 leg of the microcontroller, so we need to configure that as well. The easiest way to do this is to click on the PD7 leg in the microcontroller diagram and select the GPIO output, as we need to use this leg as an output to control the LED. After that, go back to the System Core menu and click on GPIO for more settings. You have the option to select the default logic signal level. In our case, low is appropriate because a logic low signal level is displayed on the leg during initialization, which corresponds to the off state of the LED. For the user label, it is useful to specify your own label because this allows you to manage the peripherals in the generated source code in a transparent way. For example, we can name the GPIO leg as HMI LED1 accordingly.
One important setting remains to be done. To be able to program the development board, you still need to set up the interface used for programming. This can be done on the Sys tab in the System Core menu. In the Debug drop-down menu, select Serial Wire. Save the changes. This can be done by clicking on the Save button in the toolbar, which represents the floppy disk. Then generate your code.
From now on, we will work in the main file, in the main.c file, where we implement the LED control. First, we create a variable called isTimeoutOccurred. Later on, we will use this as a so-called flag. The flag is a variable indicating the occurrence of an event. For this variable, I chose the type uint32t because we use a 32-bit microcontroller in the curriculum, so it can perform the fastest operations on this bit number. Moreover, rewriting the value of the variable will be an atomic operation in this case, which means that nothing can interrupt this process.
Before the infinite cycle, we need to make a few adjustments. We initialize the isTimeoutOccurred variable with an initial value of 0. This means that our timer has not expired yet. Clear the timer1 update interrupt flag in the counter and timer module. This is useful to guarantee a clean start and to ensure that the first interrupt handling routine actually runs after the first timer expires. Finally, we start the timer1 module.
Next, we implement the interrupt handler routine. The source code is generated and the HAL-TIM period elapsed callback function is declared, which is found in stm32f4xx HAL-TIM.age file. This callback function is called by the interrupt of the TIM1 module, in which we can handle the interruption, but we must take care of the definition of the function. Define the function in the main.c file and set the variable isTimeoutOccurred to 1 to indicate that the timer has expired.
Finally, program the contents of the infinite loop.
After initialization, the microcontroller will run this program code over and over again until the power supply is removed. At the beginning of the cycle, we check if the timer has elapsed. Let's recall, this flag is set to 1 by the interrupt handler routine of the TIM1 module, and once this happens, the if condition will be true, and the code section implemented in it will run. In this case, we will ensure that the flag is reset, so that next time we only intervene when our set timer has elapsed again. Then, we change the state of LED1 to the opposite.
We're done. Let's upload the code to our microcontroller.
Let's see. The LED is already flashing. It looks like we've successfully set the timing to 1 Hz.
Okay, so it seems to me. Don't be satisfied with the fact that your program is working. We should try to implement it with another method.
Since we've learned how the Watchdog Timer works in the previous video, why not use it? In the example, we will flash the same LED by reloading the Watchdog Timer each time the LED is turned off. However, after the 5th flash, we will stop the program from running, thereby also stopping periodically reloading the Watchdog. You will notice that the program will restart after the Watchdog Timer expires, which will be indicated by the LED flashing again.
The two examples are very similar, and since we don't want to repeat ourselves, we won't mention the clock and LED configurations. If necessary, return to the previous example.
The first major difference is that in this example, we don't use the TIM1 module. Instead, in the System Core menu, click on IWDG to configure the independent watchdog. We will set the timer to 5 seconds, so check Activated to enable the module and change the prescaler to 64 and down counter reload value to 2499.
It is important to note that the Watchdog peripheral operates from an independent clock signal with a frequency of 32 kHz.
The length of the timer can be calculated from the previous relationship. The given values are inserted into the formula, and the calculated period will be 5 seconds. In the case of Watchdog, we have limited options for prescaler. For this peripheral, we do not have to take care to set the prescaler value to 1 less, but we do have to pay attention to it when setting the counting limit.
Set up the debug interface, then save your changes and generate your code.
In the main.c file, create a counter and a WDT reloads variable. The former will be used for timing, and the latter will be used to keep track of the Watchdog reloads. Before the infinite loop, initialize the variables with an initial value of 0. Finally, complete the infinite loop. Increment the counter to count to 500,000, which is a visually noticeable waiting time, about 1 second. Once this is achieved, we enter the if condition and turn on the LED, followed by another timer, this time counting down to 0. We then turn the LED off, reload the Watchdog, and increase the value of the variable WDT reloads. All this will happen 5 times, then the program will jump to an infinite loop, which will not reload the Watchdog, letting it expire. Just before entering the infinite loop, we have done a reload of the Watchdog, so after 5 seconds, the Watchdog timer expires and the peripheral generates a restart, so we start our program from the beginning, which we can see by the flashing LED.
I'm done with the code and I'll upload it to the panel so we can see if this is what will actually happen.
Now let's see.
I have uploaded it.
The LED is flashing, which is a good sign. 3, 4, 5. Now comes a 5-second wait. And the LED is flashing, which means the Watchdog is doing its job, so we're okay.
Yes, the program has restarted. To celebrate our successful program, let us briefly summarize what we have learned in this chapter of the curriculum. We have learned about the most common modes and settings of counter and timer modules. We have discussed simple timer functions, input capture, output compare, including pulse width modulation. We examined how to monitor the characteristics of rotary motion using a microcontroller, and then turned to the Watchdog peripheral for embedded system protection. We also briefly touched on the SysTick timer, which provides an accurate time base for embedded operating systems.
We also used practical examples to flash an LED with precise timing and to see how Watchdog can protect software from getting stuck.
I hope you enjoyed the videos and gained the knowledge you sought. You can get notifications about more videos by subscribing to our channel or by following our Facebook page, the link to which is in the description. Here is also a link to our website, where you can find all the written materials and the source codes used.
On behalf of all of my colleagues, thank you for your attention. Have a nice day. Bye.
Goodbye.